So everybody, welcome again to another Airtime seminar. We're Crown in collaboration with UC Berkeley Citrus and Ben Tayo Institute are hosting these on a weekly basis. The idea is to promote innovation and give some uh, viewpoints to the outside world and some of the problems that really high-level researchers are investigating outside of the NASA fence line. And the hope is that maybe some of these ideas that you'll see across these seminars can be brought into NASA and through collaboration or grants or other funding mechanisms. But in any case, as with our speaker today, you get to meet somebody that's pretty darn smart and doing some pretty neat stuff. And feel free to interact with them after the seminar as much as you wish to. So today our speaker is Mark Mueller. He leads the High Performance Robotics Laboratory at UC Berkeley, where the research is focused on design and autonomy of aircraft. His group has expertise in building and experimentally evaluating aerial robotics. And by the way, Mark, most of the people in the room are very heavy into the advanced air mobility and UAS world right now. So they're trying to figure out how to get things integrated into the National Airspace System. Methods of interest for Mark and his team include optimal and robust control, as well as learning-based methods. Mark received his Bachelor of Engineering from the University of Pretoria, and then his Master's and Doctor of Science from ETH in Zurich, Switzerland. He is lead inventor on multiple commercially used patents and currently serves as the Associate Faculty Director of Aerospace Programs at Berkeley. There were some links to some of Mark's papers sent out ahead of time. Hopefully some of you got a chance to read them, but if you don't, they're still in your meeting invite, so you could follow up by reading or taking a look at them afterwards. And so, Mark, over to you, and thank you again for being willing to do this.
Thank you very much for the introduction, Tom. It is a pleasure and an honor to get to speak at NASA. As we were saying, sort of an auspicious day, and I think we all are looking forward to the excitement later with Artemis. But hopefully, I can share some of my ideas, and some of this will be of interest. From my side, I've interacted some amount with NASA Ames, never in a formal collaboration, but I've come down to visit a few times, and I know we've hosted many Ames folks up here on campus as well. And it's always a pleasure to make new connections. So I welcome if there's any sort of discussion, follow up here, please do send me an email or something, and I'm very open to scheduling a conversation as well. This is the second seminar I'm giving this semester, so I'm going to repeat my quick introduction here, just sort of why I'm excited to work on this stuff. So we're living in an age of transformation of mobility. I mean, a lot of things are changing, but certainly mobility is changing. How we get around is undergoing a radical shift. And I think we're looking forward to just generally mobility being easier and people being able to move around more freely. Of course, we see this with autonomous driving. One of the fields that I'm very excited about, and I know at Ames also there's a lot of energy, is advanced aerial mobility, where we have companies, Joby, Whisk, that are really pushing these very novel, different kind of aircraft with very interesting capabilities. And of course, different questions about sort of piloted versus autonomous and so on. But this promise of using the third dimension to maybe allow us to break some of the challenges that we have when you're moving on the roads. And of course, we see aerial robotics is another really exciting domain, which I think has already transformed the world. Some of it in somewhat depressing forms if we read the news, but I would prefer to focus on the more exciting things. Thinking here of things like Zipline with their life-saving blood deliveries or package delivery, or just things like photography, inspection, etc. So in all of these, I think what is really pushing these capabilities is autonomy and control. So making these systems more intelligent, creating more capable systems to deal with unexpected situations, to deal with unexpected conditions. And what I want to talk about today is two aspects that we've been working on specifically. in depth. So the first will be on some work that is trying to create a controller for adaptation to very large parametric uncertainty in the system. And this is a data-driven control approach. And the second thing I want to talk about is some of our work on motion planning in complex environments, and specifically how we tie the sensor modality to the motion planner to try and do motion planning that is aware of the sensor modality and aware of the uncertainty in the motion, and tries to create motions that somehow are more informative and then perhaps safer or more high performance, faster, etc. As well. Then time permitting, there's maybe one or two other things I'll quickly touch on, but I think these are the two big things I want to talk about. We will see that, just to sort of pause for a second, that the work we do is focused on small robots because we like to do experimental work. So for me, I really push for the students to do work that we can experimentally validate. So I want to see if the assumptions I'm making are actually, representative of the real world. And the nice thing with the small robots is we can really push these experimental systems to their limits, which you could not necessarily do at larger scale. At the same time, we are starting to work on bigger systems as well. So, I mean, we have a strong interest in taking some of these ideas and scaling them up to larger systems. So the first idea is sort of some work on learning-based feedback control. This is low-level control where we're doing stabilization effectively, and how we can use data-driven approaches to get better performance. So when we think about flight, your flight dynamics are dominated really by the physics of your system. The dynamics are really things like center of mass, mass moment of inertia, things like this. It's also going to be dependent on things like aerodynamic characteristics. These might be somewhat uncertain for your craft to begin with, but if you think about crafts that are carrying payloads, so maybe you're carrying passengers or you're carrying goods, you might not know these parameters for the payloads that you're carrying. So what we want to do is we want to create a controller or a control approach that can fly the aircraft even with significant uncertainty in the parameters, in these physical things that control the system. The way we will do this, and I'll spend a lot of time on this, but the way we will do this just briefly is we will train a neural network-based controller in simulation, and then we'll deploy this in experiment. And this is then the system that will run, and this comes from this paper that I think was shared in advance. So if you think about classic or conventional control design for these kinds of aircraft, what we typically do is we create the aircraft first. So somehow we design it and we build it, or maybe we just design it. Then we try to estimate the parameters. So we model this maybe in your CAD tool, or you start doing wind tunnel experiments. And by parameters, I mean things like the size and dimensions. Of course, these are typically designed, so there's not much estimation involved. But then you have things like the mass parameters, so the mass of the system, but also the mass distribution, the mass moment of inertia. You have aerodynamic constants, so lift and drag, things like this. And then, of course, you have the powertrain. How do I actually actuate the system? What is the model for the actuation? What are the responses of these things? Once I have my system model, I can then implement a controller. I can use MPC or an LQR or whatever approach I might like to design the feedback control for this model, and then we evaluate in simulation, and we evaluate in flight, and we iterate on this loop until we have something that satisfies our spec. This is it's obviously kind of labor intensive, and what we'd like to do is we'd like to circumvent this path and create one controller that can fly any vehicle. And by any vehicle here, let me be clear about this. I mean a quadcopter, so a 4-propeller drone. We're looking at relatively small systems. We're looking at systems that have mass, varying by a factor of 8 approximately here, right? So a small vehicle for us here that we can fly in the lab might be 140 grams, a big vehicle on the order of a kilogram. In terms of size, you might have a small vehicle which has around 50 millimeters arm length to 200 millimeters. And you can, so from this table, see that we're looking at controlling vehicles that are substantially different, right? So mass moment of inertia here differing by 2 orders of magnitude. propeller constants like the actuation of the system or differing by order of magnitude. So what we want is we want to be able to create a controller that will fly any vehicle within this set of parameters without us having to do any work of identifying or modeling the vehicle. Right? So ideally, so think of it as I want a little chip. I want to be able to glue this chip onto any quadcopter and have it fly the quadcopter without any additional engineering. Now, typically, when we think about controlling a quadcopter, you have sort of a control hierarchy where you have different layers of control. You have your outer layer, maybe mission level, position control, velocity, attitude, all the way down to force control, where you're controlling the motors or deciding what forces to generate. And then you have the motor speed controller. And then, of course, eventually you hit the physics of the system. And when you think about the control hierarchy, you can design this in this very layered approach where each of these layers is ideally somewhat interpretable and fairly intuitive. And of course, all of these depend on the physical parameters. So when we're talking about trying to learn a controller, there are different approaches you can use. One thing you can do is end-to-end learning. So what you do with end-to-end is, you can think of it as pixels to PWM, is you really try to take this entire stack, starting with the position control, ending at the motor speed control, and replace this whole block with a learned element. And this learned element, on the one hand, can be very robust because it includes, it doesn't include any of the narrow connections between state estimation and control, which is often where we see fragility enter our control systems. But it tends to be very hard to generalize. It tends to be made for a specific mission type or objective, and it's very hard to interpret anything, right? So because it's end-to-end, there's no way to sort of look inside the box and understand what it's doing. Another approach is to look at the low-level control, and this is what we will, in fact, be doing, where the low-level control is the part that interacts with the physics, right? So if you think about these different control layers, the models that they require at the position velocity level, these are typically kinematic models, right? So the derivative of position is velocity, the derivative of velocity is acceleration, and there's not much of the physics entering yet. But the physics enters very strongly in the lower levels, right? This is where, you have your controller generating angular accelerations, and then those getting transformed to torques by an estimate of inertia, etc. So what we will end up doing is we will replace the low-level control with our learn controller, this being the part where the physics is really relevant. And then we can leave the high-level control to be generic. And then what that means is you can use whatever high-level control you want. So whatever mission planner, whatever trajectory generation routine you have, you can keep using that. And you can plug it now into this dynamics agnostic low-level controller that will allow you to keep doing your mission, but do it without having to know your parameters particularly. What this then ends up looking like for us is we have our aircraft. The aircraft accepts motor commands and it generates data, of course, generates sensor data. And we are implementing the learning control at this inner loop control. The inner loop control accepts kinematic commands, so things like angular velocities, and it accepts inertial measurements, accelerometer and rate gyro data, and it generates the motor command. So this is the level of the control that we will be designing the learning controller for. And then we will close the loop with some sort of mission planning controller and some sort of trajectory generation controller, where these two things are physics agnostic. So these just know that they're flying a quadcopter, but they don't need to understand anything about the parametric uncertainty. They don't need to know about masses or inertia, etc. What's nice about this, as I said, is we can keep whatever trajectory generator you like. You can swap that in without worrying about it. What's sort of hard about this, of course, is that the inner loop control is very safety critical and it's high bandwidth, right? So clearly, if your inner loop control goes wrong, your system falls out of the sky, right? So this really is the where the rubber meets the road in a sense. This is a very critical flight component. And on the one hand, that's an opportunity because it's fun to work where you really matter, where it matters how well you do this. So this is where we will try to learn our controller. The way we learn our controller is somewhat complicated strategy, and this is a complicated diagram, so let me explain it. There are 3 phases to the learning that we do. 2 of the phases are in training, and then there's deployment. The training is all done in simulation, and the control architecture is that we have our high-level controller. This will be your trajectory tracking controller or your mission planner, whatever. This generates commands at 50 hertz, those commands being these kinematic commands. And initially, what we do is in simulation, we have access to the true parameters that we're simulating, so the true physical parameters of our system. And we learn two neural networks. We call these two neural networks the extrinsics encoder, that's the red block, the first red block, and the second element that we learn is a low-level controller. What these two networks accept, so the extrinsic encoder accepts the parameters, the true parameters that we're simulating, as well as the sensor data that the simulation is generating. And it then outputs these this vector z. Z is an 8-dimensional vector. We call these the estimated extrinsics. And the low-level controller then accepts the kinematic commands as well as IMU data and these extrinsics, these estimated extrinsics, to generate the motor commands. The objective here is to learn these two networks in parallel to get good tracking performance, so the system follows the commands well. And of course, this is cheating because at this point we know the true parameters, right? So at this point, when we're training this, the networks have access to the true physical parameters that the simulation is running. So after this phase converges and after we have good tracking performance with this extrinsic encoder, what we do is we throw away the extrinsic encoder that has access to the truth. And now we learn an adaptation module. And this adaptation module only has access to the sensor data that the simulation is generating. And this adaptation module is trying to generate extrinsics that match the extrinsics that the ground truth accessible encoder also has. So effectively, in the second phase of training, we're trying to train an estimator that only has access to sensor information, and that should estimate the same parameters as we get from the version that had access to the true parameters. Now, these extrinsics are not directly interpretable. So these are not, us saying I want to have a Kalman filter that estimates mass or inertia or something like this. These are just a vector of 8 parameters that the system in the training phase learns to parameterize the unknown physics. So we don't encode what these are. We don't give them a physical interpretation. We let the learning figure out what features matter, and those features can be some linear combination of parameters that you might interpret, or some weird nonlinear combination. We don't specify. At the end of this phase, we have 2 neural networks. We have the low-level control that we have frozen from the first phase, and we have this adaptation module. Both of these are causal and implementable. Both of them only have access to the high-level commands, the IMU data from the system, and that generate then the motor speed commands that we can send to the vehicle. At this point, we can take these networks and deploy them in experiment. So then in experiment, we can run these 2 networks and we can fly the drone. At this point, in experiment, these are static networks. So at this point, the weights in the network don't change. And this is the architecture that we then end up flying. So this feels a little bit like indirect adaptive control, right? And that you can sort of imagine you have the adaptation module that serves the role of something like your Kalman filter might have served. This then generates a state estimate that you then parameterize your, you have maybe an LQR that's parameterized in the estimate from the Kalman filter. The architecture is familiar in that sense, but important to note is that this is all without us specifying what the estimate should be, right? So we are not telling it to estimate mass or drag coefficients. We're letting it figure out what it should estimate itself, with the idea that this should be more robust, right? It should be more robust and it should be more responsive. And similarly, the low-level control, the architecture here is not specified by us, but this is simply learned. How do we learn this? So the learning approach is as follows. We have our simulation, which can generate random vehicles, and I'll speak to this in a moment. The vehicles then, the simulator will generate a random vehicle that's physically plausible. We can then run a simulation where this vehicle is tasked with flying from one point to another. we have an expert controller. And when I say expert controller, what I mean just is we have a model-based controller that has access to the true parameters of the vehicle, right? So this should be a fairly good controller. And this expert controller will, of course, generate good feedback control commands. And then we have our learning-based controller that is trying to generate commands as well. And then we can learn both in a supervised learning sense, where we can have the expert as the supervisor that generates expert level inputs, as well as in the sort of classic reinforcement learning, where we're just learning to reduce the cost. And what we do is the simulation runs. We have this rollout buffer, which is really just storing a certain amount of state action pairs, and that we can then evaluate against the control that we're flying. And in training, we start by basically behavior cloning of the expert controller, and then we sort of, with an exponential decay, reduce the weight on the expert controller and just let the learning control run from there, with this just allowing us to converge faster from this. The way we generate physically meaningful vehicles is we have, a scalar that represents, a point in, think of it as quadcopter space, right? So lambda will be this scaling factor. We scale between 0 and 1. And then what we do is we scale all of the physical parameters with some somewhat physically meaningful law. So the lambda is a length scale. So the size of the vehicle is scaled proportionally to this, I call it C here, this constant C, this uniformly random sampled constant. The mass is then scaled like the length cubed, the moment of inertia like the length to the power of 5, the drag coefficient goes like the surface area, and this then generates a vehicle. And then what we do is we take all of the physical parameters and we additionally add plus minus 15% uncertainty to that. Right? So you can think of this as basically a way of throwing a dart and hitting a realizable, or at least approximately realizable quadcopter, right? And then we generate vehicles that live in these ranges, right? So, the variation in mass of around 700%. The big number is inertia. Of course, inertia tends to be the one that scales most dramatically, but very large span of vehicles that we can create in this simulation environment. I will show you some experimental results in a moment, but first, okay, if we do this, we run it, what do we get from it? So this graph is going to iterate a few times. Let me just take a moment to explain what we're looking at here. What we're looking at here is a vehicle that's commanded to follow a trajectory. This is a 5-second slice of time, so it's not a particularly long trajectory. But we ask, if I ask it to follow this trajectory, what is the success rate? The success rate means after these 5 seconds, the final position error is within, I think, 1 meter, right? So you've somehow succeeded at flying from point A to point B. And this is for, these randomly generated vehicles, where we plot on the x-axis here the deviation from some nominal vehicle. And by nominal vehicle is a vehicle that lies in the center of that range that we have defined. And there's 2 lines that we're seeing here. The light blue line is the performance if I had access to the true vehicle parameters in each case, and I designed a model-based controller with those true parameters in mind. And of course, what I expect then is I expect perfect performance, and that's what we see here. So if I knew the true parameters of my vehicle and I used our model-based control design approach, you would be able to control every vehicle. But of course, that requires for each of these vehicles knowing exactly the parameters. The darker blue line is if I just designed the model-based controller for the nominal parameters, right? But then I fly the nominal parameter controller on different vehicles. And what we see here is as the vehicle starts to deviate from the nominal design, your success rate drops, right? So for some of these vehicles, the feedback control is not stable or is not stiff enough to keep us within the sort of tube of performance that we'd like. And this is, of course, not surprising, right? If you build the controller for the wrong physics, you're not going to get good performance. This graph now compares if I do L1 adaptive control. So the 2 green lines are different implementations of L1 adaptive control. L1 adaptive control is a fairly recent way of doing adaptive control that has found quite a bit of success in flight control. It tends to be, you can think of it as a very high gain adaptation law. There are 2 green lines here. The 2 green lines are if you do L1 adaptive control at the low-level feedback control, the way I've described we want to do the L1 control, that's the dark green line, and the other one is if you do L1 control at the outer layer, leaving an inner nominal PD controller here. So you see that, in this particular case, the L1 control is certainly much better than the fixed parameter controller. You have fairly good performance, but at certain sort of, if I vary the vehicle enough, even the L1 adaptive control starts to struggle to control these vehicles, right? So if the parameter deviations are sufficiently large. Now, if I do this learning-based control, for this, we get the red graph here. So we basically can, for every vehicle in our training set, we are able to fully stabilize and do good performance tracking of the system, right? So using this learning-based approach, we can now effectively, for every vehicle that we simulate, we can have it control the vehicle well. And this is exciting, of course. We can then ask, how much does this generalize? So here, important to note is that this is our training range. So of course, we kind of expect to do well within our training range because all of these vehicles were, or I mean, at least similar vehicles were seen at training time, right? So maybe not that exact data point, but in training, we generate a lot of samples and we expect those samples to fairly densely cover the space. So it's not too surprising that the learning control does well within the range for which we were training. But what we can also do is we can push now to see how much does this generalize. So this graph is the same graph that we were seeing here, with the variation on the x-axis again being the deviation from the nominal. Before we were seeing this range from 0 to 1, but now I'm pushing it, and forgive me for this kind of terrible x-axis, which is not to scale. But you can imagine, 0 is our nominal vehicle, 1 is sort of 100% or a factor 2 difference, but then we go all the way to factor 8, right? So we see that here we can push the variations significantly. And we see, as expected, if I use the wrong controller, so this dark blue line again is if I just have the controller that's for the nominal system, it's terrible, right? So your success rate is sort of 10%. The L1 control steadily starts to lose performance as well, right? So the L1 control starts to do poorly. More interesting, of course, is the learning-based approach that we have here, the pink versus the light blue being the expert model-based controller that has access to the true model parameters. And we see that the system, the learning-based control is fairly robust, even up to this factor 8 difference, where our success rate is still above 80%. So this gives us sort of some confidence that whatever the system is learning is actually related to the underlying physics, right? So it's not just doing a straightforward lookup table, but it has some understanding in this, very anthropomorphized sense that a neural network can understand anything, but it has some, there's in this neural net is captured some scaling laws of how these systems work. Okay, but of course the simulation are friendly, but we can also do this in experiments. So I want to show you a few videos just to show what this controller does. This first one is a fairly boring video. These are two different vehicles that we fly in our lab. These are within the set of vehicles that we were training for, but they were not present particularly in the training set. So the top vehicle weighs about 800 grams, the bottom vehicle weighs about 170 grams. And what you're seeing here is these two vehicles doing a very boring flying back and forth, but with the controller here having no access to any special data. So the controller here only knows the IMU data and the commands that we're sending the vehicle, and it is figuring out what commands to send to track this back and forth trajectory that we're flying. So that's good. We can do more interesting things. So what you're going to see here is the ability to respond to variations in flight. So this vehicle is going to fly a horizontal circle. There's two videos here. The top is the learning-based controller. The bottom is our standard model-based controller. And we will have Jerry being the sadist over here. Jerry will be adding a mass to a magnet on one of the vehicle's arms, and this mass effectively moves the center of mass. So it looks like a moment roughly to the vehicle. So there'll be this persistent moment imbalance on the vehicle. So we see here, if you attach this, of course, the mass changes, but there's also this moment offset. The model-based controller eventually does recover, so through sort of an integral action term, the model-based controller reacts, but the learning-based controller is very fast to effectively wash out this perturbation, right? So very quickly, the system can reconfigure the control and continue stably flying. You can do all sorts of other things. This is just a video that's mostly us torturing the vehicle. So this is the vehicle being commanded to hover with this controller, and then us, perturbing it. So here, shooting tennis balls at it, but also doing things like, applying a yaw torque, so yanking the vehicle around a bit. The vehicle has no data of this, right? The only thing it sees are IMU data, and it's able to sort of robustly recover from these, as we see here, recover from these perturbations. And this is, the original motivation was I want to be able to do things like, I should pause this for a second, package delivery. But more recently, we've become excited about this as an approach to do fault tolerance. So, of course, when I'm carrying payloads and I have vehicle designs that maybe I'm not so confident in, I expect to have a lot of parametric uncertainty. But potentially the more exciting case where I have significant parametric uncertainty is if I have a system that's experiencing an anomaly. So imagine, you have an actuator failure or a sensor failure or something. Your payload comes detached internally and is shifting around. So can I use this style of control as a fault-tolerant control, right? So can I use this to respond to perturbations? There are really interesting questions about how does one go about certifying this? How do I go about maybe convincing the FAA that something like this should be allowed for a flight controller? But the potential advantage is a controller like this can be made to be robust to a large set of possible faults. And you can do this by looking at the effect of the fault rather than the cause of the fault. So potentially it allows us to create feedback controllers that are fault tolerant without requiring the fault identification tree, right? But just in effect responding to the effect of the fault, and allowing you to then create systems that have some amount of fault tolerance without requiring the complexity and potentially additional sensors that a more conventional fault tolerant strategy might have, right? So there's this question of maybe you can do something that gives you just extra capability. So what this video is going to show you, let me just explain it before we see it. This is us simulating an actuator fault in the vehicle. So this vehicle is going to take off, but what's special is that we're going to have this front left propeller from the vehicle's perspective, or just the front propeller from our perspective. We're going to have this propeller with reduced effectiveness. So I think what we're doing is we're effectively in software, without the controller knowing about it, of course, we're reducing the effect of that actuator by 50%. So it's like half of your actuator being damaged. And we're going to compare the performance of our standard model-based controller on the left to the learning-based controller on the right. And the learning-based controller has not been modified at all. This is still exactly what we have seen before. So we see what does this look like in flight? So the model-based controller, has less force than we would expect. So you kind of see the vehicle pitching forward and failing. But the learning-based controller initially has the same problem, right? So initially it does have the vehicle pitching and rolling, but then very quickly it is able to identify, not identify the fault, but reconfigure the control to accommodate the fault, right? And to compensate for that initial uncertainty. And this is something we are currently very excited about, and we have some initial work with Joby where we're interested in trying to use some of these ideas with some of their aircraft. But I would be excited about potentially collaborations with NASA as well on ideas like this, right? So pushing this fault-tolerant control in new, learning-based control for fault tolerance, maybe allowing us to create more capable systems that can react faster and potentially have a single layer of control that is just capable of more and might even be easier to certify because it's only one component. You're not reasoning about a complex system. Okay, so that was the first half that I want to talk about. The second half I want to talk about will be more higher level planning, and this is our work on perception aware planning. So here, basically, when I'm doing motion planning, how do I account for the sensing modality? How do I account for the uncertainty that I have due to my sensing modality? And how can I do motion planning that is better for this. So what do I mean by all of this? So if you think about a classic robotic approach to flying through, autonomously fly through complex terrain, if you have your AAM aircraft that's trying to land, how do you do this? Well, a classic control strategy might look something like this. So you have your agent, you have a tight inner loop. The tight inner loop might have a state estimator and some sort of low-level control that's aiming to stabilize the system. And then you have an outer loop. The outer loop will do things like mapping, right? So it will consume, camera or LiDAR data and build some map of the world. And then you have your global planner, which takes the map of the world and generates a reference trajectory inside this map. That then gets sent to the low-level control that then executes this map, sends commands to the robot, etc. Right? So this will be the typical loop. And on the one hand, this is nice because as an engineer, these are 4 well-defined blocks that I need to design with clear interfaces. So it's sort of typical design and divide and conquer approach. The problem with this is that there's a fragility that happens when the mapping especially goes awry. So if the map that I'm building of the world has a mistake in it, so I have a false loop closure or something, and I have a map that does not represent reality, generate a plan through this map, and tracking it might lead to disaster because that map is incorrect, right? And the fragility happens in these connections, especially this connection between mapping and planning, where I am, this connection leads potentially to issues. So what we've been interested in is modifying this loop somewhat by putting more intelligence in this tight inner loop. So what we want to do, and what I want to talk about today, is have a local planner that is more informed about what the world around it is doing, and through that is able to act in a more safe fashion. So we will have a local planner here that replaces the low-level controller. This local planner is tasked with this safety-critical collision avoidance of the vehicle in the local environment. And what that means is that we're no longer as sensitive to errors in this outer loop. So if the outer loop comes up with an inconsistent map and a trajectory that would collide with something in the world, the local planner will be able to do the obstacle avoidance either way. Now, the challenge here is that this local planner needs to be very fast. It needs to be able to run as fast as our feedback loop, right? So we are much more sensitive to timing here. And we're very sensitive to errors in state estimation, etc. So the approach we use to this is we're interested in things that I can sense on board. We really like to use depth cameras. LiDARs would be another technology that's fundamentally very similar. What these give us is they effectively give us a 3D world, a 3D map of the world around us. And they do this at a very high update rate. And they do this in a memoryless fashion. So each frame of your LiDAR or of your depth camera is a local map that's valid at this instant, and at the next instant I get a new frame. And if there had been an error in the last frame, that error does not permeate into the present, right? So that error does not stay. The challenge is in making a planning algorithm that is fast enough to run at the same rate that these things run, right? So doing motion planning in complex environments is expensive. So we have an approach that has to do, and I'm not going to spend too much time on this, but it has to do with parameterizing the motion as polynomials, and then we can do motion planning both for input feasibility as well as collision avoidance very quickly using these polynomial trajectories, and then we can do a random sampling-based search through the environment to do this local planning. So the effective idea is I have my vehicle, I see the world. So imagine this is maybe what your depth camera sees. You have some obstacles. Your depth camera knows that this white area is obstacle-free. And then what you try to do is you try to generate a trajectory that flies you towards your goal. Your goal is, in this particular image, flying towards the right. And we have ways of very quickly, if you generate a potential trajectory, very quickly evaluating whether this is collision-free or not. Okay, and then in this random sampling way, you generate many random samples. You find the one that is collision-free, moves you towards your target best, and you execute a little bit of that trajectory in an NPC-like way. The vehicles we use, these are our experimental drones. We have some co-computer. In our case, it's typically a Qualcomm board that's running ROS. Then we have our flight controller. For us, it's a modified PX4. Then we have our sensor. We like to use the Intel RealSense cameras. These are just very easy to integrate. And then we do visual inertial odometry through VIO, OpenVINs, to do the state estimation. Now, if all I do is I do motion planning and state estimation separately, you get something like this. This is a project we did with Army Research Lab, where the objective was fly through this forested environment as quickly as you can from one side to the other. And what you're seeing here is this algorithm running where the perception is running and the motion planner is running, but these are running separately. And the motion planner is just trying to fly from point A to point B. In this video, you see here Shangyu. Shangyu is the safety pilot. He has a joystick in his hands, but he's not doing anything except he has to be there to turn the vehicle off if it does something really stupid. But the vehicle is fully autonomous. And you see in this sort of inlaid picture, you see the perspective that the vehicle has. And what we found is this tends to work very well. And initially, we thought that the speed with which I can fly will really be dominated by my acceleration capabilities. But it turned out that we were really dominated by when the motion becomes too fast for the inertial odometry system to track where we are. So what happens is our vision system loses track of where the drone is, and then you crash because your system state estimate is going wrong. So we're interested in this idea of, can I do motion planning that is perception aware? Can I somehow imbue the motion planner with not just knowledge of collision avoidance and input capabilities, but also with an understanding of how the perception system works so that the planner can generate motions that reduce uncertainty, right? So that give me more information. And what's nice about it, if you do this well, is you explicitly can encode the trade-off between speed of flight and robustness. So you can imagine, if you want to go from point A to point B quickly, the camera might see a lot of motion blur. It might not be able to track the visual features. And for that reason, the performance might be worse than if I were to fly a little slower. And if the motion planner can be aware of this trade-off, it can do this explicitly for us. Looking at the clock, I'm going to have to speed up slightly, so apologies if I speak quickly. The way this works is the motion planner is tasked with going from whatever its current state is in the world to some goal position. So imagine this is our world. There are some obstacles, maybe these are trees, and my objective is to fly from my current position to the goal position. We will do this using this randomized sampling approach. So we'll generate different polynomial trajectories. But what we're going to do now is we're going to also give the motion planner access to the visual features that the system is tracking to keep track of its own state. So these gray dots are the visual features that the VIO system has seen and that it is going to use to do state estimation as we are moving from the start to the goal. And our motion planner can then take these two possible trajectories, the red and the black as candidates, and not just evaluate how fast we're moving towards the goal, but also how much information would the system get from the visual features that it is tracking, but also what is the motion blur that we expect to see as we're flying from point A to point B. The motion blur, of course, being a function both of the linear speed of the vehicle, but also the angular velocity. And each of these candidate trajectories, you can calculate as you're flying along it, how much information you get. And then we can combine these two to compare them and choose the best trajectory. And we can do this, of course, for many possible trajectories. We can sample fairly densely, and then we can choose the best sample that we have found, execute a little bit of that trajectory, and then fly a little bit of the trajectory until we have more information. I'm going to skip the motion blur part, but the algorithm is effectively, at the current time, right, take an image of the world, a depth image, generate possible trajectories that fly through the world, make sure that each trajectory is collision-free and input feasible, then check for each possible, for each of these candidates, check the perception score, so how much information am I gathering as I fly it, and then retain the best candidates, right, until I hit some timeouts. In our case, we're running this at 10 hertz, so I have 100 milliseconds to do the sampling. And once I hit this timeout, I take the best trajectory, execute 100 milliseconds worth of flight, and then at the next instant, I will get a new camera image, and I can just repeat this process. So it's a sort of model predictive control receding horizon planner. And each of these candidates is designed to end at rest. So it terminates at standstill. So in the worst case, if I were to fly into an environment, let's say I fly into a tunnel and the tunnel is blocked, this is guaranteed to terminate safely, right? So this is guaranteed to come to rest in a safe condition And of course, we might get stuck. The planner might get stuck at a certain point, in which case your higher level control will have to kick in with the global map of the world to get you unstuck. So all of that's a long explanation. What does this look like? So here's a little video that's going to show the drone taking off and flying down the road. I'm going to show two videos. The first will be if I just have the planner with the objective of flying from start to finish as fast as possible, but ignoring the perception system. And the second video will then be the perception aware. The video is showing the starting point is here. The end goal is 30 meters down the road. You're seeing two inlaid pictures. The top is the depth camera. So this is our image of the free space around us. The bottom is the black and white monocular camera that we're using to track the state of the system. What you're going to see is the vehicle take off, and the objective is just fly down the road, and it'll fly a more or less straight line down this path. Because there are no obstacles, it can fly more or less a straight path just from point A to point B. Now, it's not perfectly straight. You see the vehicle sort of maneuver slightly to the left and the right, and that's just because of the random sampling, right? So sometimes, the random samples will be slightly to the left or to the right. And of course, it makes sense. If you ask me to fly through empty space from point A to point B, I'm going to try and fly a more or less a straight line to do that. Now, if I do this alternative planning approach where I have access to the state information, what we'll see, oops, why is this not playing? What we'll see is the vehicle flying a motion that's going to fly close to these obstacles on the left-hand side. These obstacles on the left-hand side have much more visual information than the street. The street has very little visual information. So by flying towards these obstacles, the system can gather more information and has more information to do state estimation. So we'll have a better state estimate when it arrives at the terminal condition. So we see here this behavior where the system explicitly trades off some flight speed to accomplish a higher information and to have less uncertainty. And we can verify this by looking at estimator performance. But maybe I will skip what I wanted to say about other things and leave some time for questions. This is the feedback form. So I think if you scan this, it'll bring you to a feedback form. But maybe I'll stop here and then we can have some discussion as well. So thank you very much for your attention.
Thank you, Mark. That was actually really interesting, I thought. So let me open it up to the floor. I knew Michael Abramson would have a question. He always does, and they're usually good ones. So we'll start with you, Michael. Go ahead.
Thank you. It's a fascinating work, and I have a couple of questions. One is related to your slide 10, if you can.
Let me put it up. 10 here.
Yes. So this feedback from your low-level control to trajectory control. So whatever trajectory generator you are using, even if it's purely kinematic, it still needs to know something, right? So like accelerations, limits for vertical speeds, and so on. So is it what you provide in this feedback to trajectory control?
Yes, you're calling me. I was a little glib here. So your trajectory controller cannot be totally agnostic to the vehicle, right? So you need to have. So certainly we give it some sort of acceleration limit that it has to respect. So this has to have some knowledge of the system. Yes. Okay. So we give it explicitly. We give it sort of. Let me think that I'm not lying. I think in this experiments we were showing, we give it. Acceleration limits, not velocity limits or anything like that, because we're only evaluating it for relatively short motions that were not too fast, so the velocity did not particularly matter. But if you were doing something where you're moving at high speed, you probably want to add additional limitations to it, yes.
Okay. And now, can you please get to your slide 29?
Okay. This one here, I think.
Yeah. So in this context of collision avoidance, how many trajectories or candidate trajectories you are generating, and what is the logic behind of generating this trajectory? So are you considering, for instance, different dimensions like horizontal, vertical? So how are you doing this?
Yeah, so that's a good question. So the exact number of trajectories, I'd have to double check. It's on the order of 1,000 to 5,000 candidates that we evaluate at every time step. But let me just, the trajectories are generated starting from your system's current state. In this context, that's position, velocity, and attitude. And we sample a final state which is in three-dimensional space. And it's at rest, but we sample 4 parameters. So it's the 3D position where you come to rest and the duration that you're allowing the trajectory until it hits that rest. These things, the initial condition and final state and trajectory, fully define a polynomial. And then we evaluate that polynomial for cost. We evaluate that polynomial for input feasibility and collision feasibility. And we compare on the order of 1,000. Most of them get thrown out because of collision or they have a higher cost or something. So we don't necessarily fully evaluate all of the 1,000 that we generate. But effectively you're searching in a sort of set of 1,000 samples in a 4-dimensional sample space.
Okay, thank you.
Right. Are there other questions from anybody? I have one. Doesn't look like it. So, Mark, I'm just, hopefully I don't say something stupid. But as I'm watching and I'm thinking like how would I use it in my world? And so I'm thinking, you said you were working with Joby and maybe you haven't talked to them about this, but I think they and others are going to have a complex environment in a cityscape, approaching buildings that they may have a map or a visual storage of what they will see. But you have wind gusts that cause a disturbance as they're approaching the top of a building, that you have to stabilize the aircraft very quickly in order to hit this very tiny spot. I imagine you guys have thought of that problem, and it seems to me like what you're doing, especially when you're joining the visual image with the stabilization model, that maybe you could be helpful there. Does that make sense, what I've asked?
Yeah, I think so. Certainly one of the things we've sort of been toying around with, but don't have any results to present yet, is on things like wind and gust estimation and rejection. And you can imagine in the AM sort of context, you have both just complex wind environments near the ground because the buildings might be tall and they might be in the shadow of things, etc. But also you're operating these aircraft at low speed, so you are more sensitive to gusts. So it's sort of an interesting problem area. I think it's an exciting space to work in. One of the things we're interested in is, to what extent can I estimate the current wind and the gusts from, say, maybe just sort of the IMU data that I have or something like that. On the one hand, can I do better than an array of pitot tubes or something like that? But also, can I be more robust, right? So if I, the pitot tubes, it's they can get blocked by something or whatever, right? That just stuff can go wrong. So if I have a way of generating redundant estimates that might make a safer system, but also this is more speculative, but if I have a 3D model of the world, can I do some sort of maybe fast CFD or something and predict what the disturbances might look like? Maybe predict where would be a trajectory that is less likely to be perturbed. So what is the approach trajectory that is more comfortable for the passengers, etc. I think these would all be very interesting things to try and think through.
Yeah, I like what you just said there. I think the other thing, and I imagine people have thought about this, but when I talk to airline pilots earlier in my career, they would sometimes tell me stories of they're on an instrument approach into a major airport, and when they actually break out and see the runway, it's not exactly where they expected it to be. They have to turn the airplane quickly or descend quicker than they thought or something. And I imagine that some of the work you're doing might have application there as well, because this will certainly happen as well in lower visibility operations mostly if you think about landing one of these these AAM aircraft, these Joby or Whisk or
Yeah.
whatever aircraft, they if you're thinking about landing them at an airport, even a small airport, you have lots of room to be not quite right. But
Yeah.
when you're in an urban landscape, it might not be so simple. So yeah.
That's so one of the projects we've just started. We have a project funded by Boeing, which is trying to use some of these ideas. For now, we're looking at operation on the taxiway, but I think we would be particularly interested in sort of landing. And I mean, we had the accident last week, the fatal accident at LaGuardia,
Yeah.
right?
Yeah.
Where the question is, can I detect things that are not where they're supposed to be? But from my perspective, I'm very interested in exactly this kind of thing, where how can I do, if I have uncertainty, can I adapt my motion to maybe reduce that uncertainty, right? Or sort of trade off uncertainty with performance? Is there a way that you could, you say there's something potentially that's going to intrude on my trajectory? I'm not sure what it is. How can I hedge my risk and maybe, gather more information so I don't have false positives all the time, right? You don't want to always be doing emergency behavior when it's not necessary. But I think this is something that in the AAM world, as you say, because it is much more constrained. And also, you're looking at this incredibly high pace of operations. If you're actually going to do this, it has to be, very high throughput situation. So how do you do that well? I think so very interesting and hard questions to answer.
Yeah, there's a lot of interesting stuff, and I think it's good that you brought up the LaGuardia accident, because I think about, I'm not an AI expert by any means. I'm too old for that, but I can imagine that there's things that visual recognition and fast learning and all that stuff could possibly have helped there.
Yeah.
To recognize that something wasn't quite right. There's always a trade-off between overreacting to something that'll be fine because the fire truck could have stopped, even though
Right.
it looked like it was moving towards the runway. And how to, how does a learning system adapt to that? Because 999 times out of 1,000, that truck will stop and wait.
Right.
But
yeah, I mean, look, some of these will always be, there will always be the case where nothing you do will there's nothing you could have done, right? And I'm not sure that one could have been prevented, but it certainly reminds us, and the complexity here, and the pilots and the limited visibility that they have, and the complexity of these systems. If you can make something that at least might give you some more information. But especially, if you think about Whisk, which is wanting to do fully autonomous flight, how do these systems have to make these decisions, right?
Yep. It looks like Michael has another question. We probably have to wrap it up soon, but go ahead, Michael.
It's rather a quick comment related to this accident with a fire truck collision. So what is critical here is what do you know about intent of another vehicle or another aircraft? And somehow you have to factor this in at some point. So,
right.
I think I've heard some discussion that if you have a large language model that's able to interpret what the controller is telling everybody, it possibly could have picked up that we were pointing towards a disaster. Because you have ADS-B data about the aircraft position, I guess the truck didn't have ADS-B, but you have some knowledge of its location, and then the controller instructions, which was managing both the aircraft and the fire truck, he recognized very quickly that he made a mistake. And I don't ever think any accident's one person's mistake, but he very quickly realized and tried to stop it and then said, I messed up. So the question becomes, could a language model have understood what was happening and, knowing the trajectories of both vehicles, figured it out? I don't know.
But would not the likelihood of large language model hallucinating be more than the uncertainty of this other factor? So I would not trust much to large language models. Although I agree with your general point that from aggregating this information, you could get it better, but.
Yeah, and then the other accident that seems like presents an interesting problem to look at is the helicopter airline crash at DCA a year ago. That also had some things involved that maybe some AI tools might have been helpful with. Okay, are there any other questions from anyone else? I don't see anybody's hand raised.
If not, feel free. Please send me an email. I'm fairly local, so happy to discuss.
Okay, and then for the people online, the next seminar will be next. I believe this is, well, April 7th. I think that might be Tuesday at 11 a.m. Yasenko Rakas will be back to talk about multimodal monitoring of pilot controller communication and intent for aviation safety. I think I've seen her talk about something related to this before, so I think if it's what I think, it should be pretty interesting. Everybody, Mark gave you the link, and I think it's in your invite as well for feedback. We actually do use this and provide information back to the speaker, but also in helping to shape future seminars as well. So please fill that information out. And thanks everyone for attending. Thank you, Mark, once again. I really
Thank
enjoyed
you.
this one, to be honest. So
Excellent. Thank you all.